Hi everyone, I'm Alessandro. I'm here to present our latest work, Lagrangian Decomposition for neural network verification. Let's first motivate verification through an example. Let's take an image of a panda. This is correctly classified by a neural network. Let's add some noise on top of it and rescale it down so that we get another image of a panda. This time though, the network is very confident that this is a monkey. This is a classic example of adversarial vulnerability. And we're interested in proving or disproving that this property holds. We do this through verification. This means feeding an image to the network, along with a specification for its input domain. This might be a ball in L infinity norm of the allowed perturbations around the image. And for each layer, we want to compute the set of the allowed activations under the input. We do this for all of the network layers until we get to the end. We now have a specification of the set of all possible outputs. We want to make sure that the property holds for all the points of the set. If it does, then the property is satisfied. In this case, it is. All the points are correctly classified. Unfortunately, though, this is NP hard due to the nonlinearity of the network. We therefore tackled something easier but faster to solve. We approximate the network through a convex relaxation. Same input domain, we compute the activation sets. This time, they're all convex. They're approximated by convex supersets. We finally get to the output set, and we're still able to prove that the property is satisfied. Unfortunately, though, we're not going to be able to do so for all the images, only for a subset of them. We're going to be able to do it much faster. So verification can be seen as an optimization problem. For networks, it looks like this. We're minimizing the last layer output given calligraphic C, the input domain, the linear parts of the network, yielding the hafted variables, and then the nonlinear activation sigma. This nonlinearity is source of trouble. So to make the problem easier, we approximate the minimum through its lower bound. This has been done extensively in the literature, but here we're mostly interested in a specific previous work that was obtaining the Lagrangian relaxation dual of the network and solving it iteratively. We call this DSG+. Our method is closely related to this and relies on Lagrangian decomposition. So decomposition is a technique known from the 80s, also known as variable splitting. Its main advantage is that it yields better or equal bounds with respect to Lagrangian relaxation. So we apply this in our original non-convex problem, but first we convexify. We substitute sigma by its convex Palma. For Aurelie, this means filling this green triangle. This is called the planet relaxation. So we now have a convex optimization problem, and we apply decomposition. So we split the variables, set an equality constraint so that the sets are equal, and then relax this newly added constraint to obtain the decomposition dual. The advantage of this problem is that the optimization decomposes perfectly over the layers, so we can solve this relatively efficiently. Theoretically, thanks to the results obtained in the 80s, we can prove that our decomposition dual dominates the relaxation dual presented previously. So for any dual solution to the relaxation, our decomposition dual yields a better or equal bound. We can exploit this in a number of ways. The first is a direct application of the theorem. So we solve the relaxation, obtain a dual solution, and plug it in the decomposition to hopefully get a better bound. Alternatively, we do supergradient descent directly on the decomposition dual without an updates, or finally, we do proximal maximization on the decomposition dual, yielding the augmented Lagrangian method. For technical details, please refer to our paper. Implementation-wise, we employ PyTorch, and this allows us to exploit both massive GPU parallels and also the convolutional structure of the networks. For our results, we compare against DSG+, so add them on the relaxation dual, the method by Wang and Coulter, the closed form dual assignment corresponding to a specific dual initialization of our decomposition dual, Rudy. So we use the commercial state-of-the-art LP solver to solve the LP given by the planned relaxation, and the time-limited version of this. So to assess the quality of our bounds, we want to minimize an upper bound on the margin of robustness of the networks to adversarial perturbations. We do so on networks adversarially trained on cipher 10 coming from the Wang-Coulter paper. We now look at the bounds from left to right. We can see that Gurobi yields the best possible bounds, but it's very slow, more than magnitude more than the other methods. Time limiting it does not yield significant differences. It is still very slow and yields very loose bounds. The method by Wang-Coulter is very cheap, but yields very loose bounds. DSG+, so Adam on the relaxation, is somewhere in between. So this yields quite good speed accuracy trade-offs. But by direct application of the theorem, so the green plot, we can improve on these results. We can further improve on the theorem by solving the decomposition problem directly with supergradient. And finally, proximal maximization on the decomposition yields almost optimal bounds in only a fraction of Gurobi's time. We can look at these results more closely. So here we compare supergradient on the decomposition versus supergradient on the relaxation. This is DSG+. We can see that the time on the left is roughly the same, but supergradient, so Adam on the decomposition, yields consistently better bounds than DSG+. The same reason holds when comparing proximal versus supergradient. Proximal yields better bounds at the same time. Finally, we want to employ our bounding methods in the context of complete verification. To do so, we use them as a subroutine to a branch and bound framework from our previous work, and we try to verify that some cipher 10 images are robust for a given network to adversarial examples. There are two main takeaways. The first of them is that using these looser bounds is still an advantage because they're very fast to compute and they can exploit GPU parallelism. Moreover, better bounds correspond to better performance. Proximal is better supergradient is better than the previous work, so DSG+. All of them are much faster than Gurobi-based methods, so solving the MAP and using Gurobi for the bounds. So we presented Lagrangian decomposition-based algorithms. They dominate previous approaches theoretically and in practice. They offer a wide range of speed accuracy trade-offs. They can exploit parallelism and convolutional structure. In this future work, we plan to use the same approach for tighter and more complex relaxations. Thanks for your attention.